Hello, this presentation will be showing a seasonality model of the coronavirus. I decided to model the coronavirus for my end-of-year machine learning project. Before I go into my model, I will be talking about some background information regarding the virus. COVID-19 first emerged in Wuhan, China in early December of 2019, but it was not until February of 2020 when the first cases appeared in the United States. By mid-March, all 50 United States and its territories had confirmed cases. All types of the coronaviruses are known for attacking the respiratory system. While they do oftentimes have similar symptoms to that of the flu, the more severe cases can lead to respiratory problems, kidney failure, and death. Coronaviruses are also commonly found in animals, but it is rare for them to infect humans. The virus is spread through water droplets leaving the host's mouth or nose through a cough or sneeze. They will usually only stay in the air for a few seconds before falling onto surfaces, where they can live for a few days. One of the two previously known bad cases of a coronavirus outbreak was the SARS coronavirus, also known as SARS-CoV. SARS stands for Severe Acute Respiratory Syndrome. This outbreak occurred in China in November of 2002, soon spreading to other countries. China did not notify other countries until February of 2003. Coronaviruses usually have one animal that they originate from. For SARS, that is the horseshoe bat. The SARS outbreak ended in 2004 with the total number of cases being 8,439. 21% of these cases were healthcare workers. There were also 73 United States cases. The total number of deaths was 812, with a 9.6 fatality rate. There is no known vaccine or treatment. SARS does have seasonality, which is what I'm predicting COVID-19 to have. COVID-19 is also known to spread much faster than SARS did. The other major outbreak of a coronavirus was the MERS or MERS-CoV outbreak. MERS stands for Middle East Respiratory Syndrome. MERS was first reported late in 2012 in Saudi Arabia. Only 27 countries have reported cases of MERS since the outbreak, and 80% of these cases occurred in Saudi Arabia. Unlike SARS, this was a zoonotic virus, meaning most cases of infection spread from animals to humans, with the main host animal being the dromedary camel. MERS did have similarities to small European bat coronaviruses. MERS had a total of 2,519 cases and 866 deaths, with a fatality rate of 34.3%. There were only 2 United States cases of MERS. MERS, like SARS, has no known vaccine or treatment. The COVID-19 is the third major case of a coronavirus. COVID-19 stands for Coronavirus Disease of 2019. This version is the most widely spread coronavirus, with cases reported on every continent outside of Antarctica. COVID-19 is caused by the SARS-CoV-2 pathogen, which has a close resemblance to SARS-CoV mentioned earlier. As of May 12, 2020, there were 4,312,750 cases in the world, with 290,946 deaths. The United States has 1,395,027 cases, with 82,555 deaths. So far, the United States has the largest number of cases and deaths outside of China. The fatality rate is 1.38% to 3.4%, depending on the country, with an incubation period between 3 to 14 days. There is no known vaccine or treatment at this time, although the coronavirus is more infectious compared to SARS and MERS. Both SARS and MERS have much higher fatality rates than COVID-19 does. So, based on the information I gave earlier, I was interested in seeing if COVID-19 would have a similar seasonality path of that of SARS and the Spanish influenza, which up until this point was the deadliest pandemic in history. It infected a third of the world's population and killed at least 50 million people. In the figure below, you can see that there were 3 waves of the Spanish influenza, the first of which started at the end of June. The second and most devastating wave occurred in late September and lasted until early January. The third case occurred in early February of 1919. Now the coronavirus for the United States started in early February, so it will be interesting to see how it changes this model. I will be using the known SIER or SIER-CD model that has been widely used in the medical industry to track virus outbreaks and view their potential damage. It is most commonly known for predicting the HIV and AIDS outbreak. SIER or SIER-CD stands for Susceptible, Exposed, Infectious, Recovered, Cases, and Deaths. The input parameters are sigma, which is 1 over the incubation period, gamma, which is 1 over the duration of contagiousness, R naught, which is the reproduction number, and beta, which is the infection rate. So my first step was trying to implement seasonality into the model. I wanted to make sure that I could get the waves that I predicted using a sine function. So I started without fitting the model to the data. The figure below shows the output from this step. As you can see, the model produces an output that is very similar to that of the Spanish influenza, where the second wave is much larger than both the first wave and the third wave. In this figure, you can see where the data starts in relation to the sine curve, shown in the red circle. So because the Spanish influenza started so much later than the coronavirus 19 did, I knew that there would be a different outcome when I fitted the model to the data. So once I fitted the model to the data by using an error function to calculate the difference between the expected number of cases and deaths to the actual number of cases and deaths, I then used the MATLAB function fminsearch to find the best starting points for my model so it fits to the data more accurately. At the end of the fitting process, the model does not produce any waves after the first wave. One theory as to why this is because the virus has more time to eat through the population due to its several-month head start over the Spanish influenza. So during the time I had just finished implementing seasonality into the model, news reports started coming out saying how several individuals had contracted the virus several times. The first of these cases happened in China, but soon more people were getting the virus twice. So I decided to see if adding a new parameter with the number of days a person is immune for into the model would make a difference. This is the part of my code that I changed to incorporate both seasonality and reinfection. Highlighted in blue is the change for seasonality, and yellow is the reinfection. So I added in a new parameter, IM, which is the number of days someone is immune for, which I set as 120. My first step was to take the number of people recovered and divide that by the number of days they're immune for. We then subtract that number from the number of people recovered, x.4, and add that to the number of people susceptible, x.1. This makes it possible for people to travel between the recovered class and the susceptible class. Once this is implemented, we start seeing the expected waves of seasonality that I predicted would be there. As of April 21st, 2020, this is what my model was predicting. As you can see, there was going to be a fairly small wave predicted in the fall. This is the model based on the data through May 12th of 2020. As you can see, the second wave is drastically larger than it was in the April 21st model. The only thing that I changed between these two models is the data. The April 21st model only has data up through April 21st. The May 12th model only has data up through May 12th. The model changes because it's fitting to the data. the model will continue to move around slightly until the pandemic is over. But this is a closer look at the model. In the image on the left, you can see a closer view of all 3 waves. I'm focusing on these 3 waves because it takes around a year for a vaccine to be created, but this does not mean that there won't be a possibility of waves coming after these 3. On the right, you can see how close the fit is between the actual number of cases and deaths to the predicted number of cases and deaths. After using my model on the United States data, I decided to see how other countries could compare. The first country I decided to look at was Germany because I heard that they had a strong hold on the virus and were very strict with their regulations. As you can see, they had a very small second wave being predicted for the fall. They also have a smaller wave being predicted for next spring. This is a closer look at the model with Germany's data. Even zoomed in, it's hard to see the second wave. This model looks different from the United States projection because the data is different. The model incorporates the data into the model to find the best fit based on the data. So because each country has different data, each country will have a slightly different model outcome. Again, the only thing changing between these countries is the data and its starting population, which correlates to the country's population. The figure on the right shows how well the model fits the data. The second country I decided to take a closer look at was Italy, because they also had very intense regulations put into place to protect its citizens. As you can see, this model looks very similar to that of Germany's. The slight difference is the first wave is just a little smaller, and the second wave is just barely visible. If we look a little closer, we can see all waves a little easier. Again, we can see that the model did a very good job of fitting the actual number of cases and deaths to the predicted number of cases and deaths. The last country I was interested in looking at was Russia, because they had been having a very large amount of new cases daily, more than the United States has been having. As you can see here, circled in red, Russia had over 10,000 new cases, while the US had a little over 9,000 new cases. So after running my model with the data on Russia, you can see the drastic differences of this output compared to other countries. This is the first model that produces a larger second wave over the first wave, which is a little bit surprising. But based on the first case, which according to Johns Hopkins was in February 1st of 2020, and the number of cases and deaths per day, the model produces a much larger second wave compared to the past 3 countries. When we look closer, it makes it even easier to see how much larger the second wave is compared to the first and third waves, making the Russia prediction the most similar to the Spanish influenza seasonality. Again, on the right, you can see how close of a fit the model is to the actual data. In conclusion, when I added seasonality and reinfection into the SIER model, it produced future waves of seasonality in the spring and fall of each year. As for my original hypothesis that the COVID-19 would have seasonality waves similarly to that of the Spanish influenza, the Russia prediction was the only one that follows this theory. The other countries, Germany, Italy, and the United States, all produce a similar effect with slight variations, where the second wave occurring in the fall of 2020 is smaller than the first initial wave, but the other countries I ran the model for did produce seasonality waves. As a disclaimer, these are just predictions. We will not know the exact outcome until it comes to pass, but hopefully models like mine can help influence change so the death toll won't be as high as originally predicted. All of these models were run on the data from Johns Hopkins as of May 12, 2020. These are the references used for my background information, seasonality implementation, and my data. Thank you for watching.